Okay, okay, okay.
Again, no need to call me sir. I'm just a PhD student, just like you.
Ultimately, you are teaching us, so that's why.
And no, 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 not nothing like that. Don't think like that. So I hope you can see the screen. So
Yes, yes.
um, welcome to week 3 live session of molecular spectroscopy of physical chemist perspective. So today what our agenda is that we will uh, try to solve the assignment 1 and 2 problem, as I think the submission date already crossed, so we can discuss the problems if you have any particular uh, query regarding the questions, and then we'll move to discussing the numerical problems from vibrational spectroscopy, specifically infrared spectroscopy, right? And if you have any doubt, acha, on the previous day, you have asked me one thing. I think I have not given a proper answer that time. That what is the effect of non-rigidity on the spectral behavior? What sir has asked. Maybe when we have seen the first lecture of week 3, I think your doubt has cleared.
Yes,
So
yes.
yes, so if I have the Banwell open, let me show you. So this was the part we were discussing, right? That when it will become non-rigid. So that time, what will happen? This perturbation thing will come into the energy. So the energy will look like. So there will be a term added to the energy. Earlier it was B into j plus 1. Now extra term is there, centrifugal distortion constant d, and d is related to the d has some value, like just like you already knew that b is a rotational constant, so d is centrifugal distortion constant and d has a specific value. Don't try to mug it up, then it will be difficult. Maybe the value will be given for a numerical problem. Just remember the unit is in centimeter inverse, just like B. Okay. And when you put this D into the energy term, now when you are measuring the difference between the energy, it becomes 4D into J plus 1 whole cube. And the main thing is that earlier your difference in energy was 2B into J plus 1. Now another term has added, but this term will be significant. So first of all, D is very, very small, the smaller than B. Okay. The one thing is that now, so this will decrease your difference between the energy when the value of J is very high. So when J is like 0, 1, 2, 3, 4, it will not affect much. When the value of J is significant, that time your difference in energy, that part will be decreased much compared to the rigid rotor. So this is how the energy spacings will look like. See, when the J is very small, that time the change is not much. But see, when J is 10, then so this is for a rigid rotor and the right hand side is for a non-rigid rotor. So here your bond length can change. Now what is happening that your this energy is decreasing. So obviously the difference between the energy is decreasing. That's why you can see in the spectral line, the gap is not same anymore. Earlier, the what was the gap? 2b, right? So from where we calculate the bond distance, that is not same when the J value is higher. So for this transition, the energy levels are not equispaced anymore. So the upper panel is showing for a rigid, non-rigid bond, and the lower panel, as you can see, the energy spectrum has red shifted. To be honest, see the red shift and the blue shift we talk it about in the sense of lambda wavelength. So if energy is decreasing, then it is
Red
in
shifted.
wavelength
Yes,
scale redshifted.
yes.
So these are just a few points, the redshift and blueshift, and there is a relationship between your omega, I should say the frequency square to that with your rotational constant and centrifugal distortion constant. So this equation you may remember, but you don't have to remember this long thing. I hope in examination, if something will come, they will give you the value. Okay. So okay, anyway, and is also constant a term, this force constant. Okay, this you are going to see also in the I guess in the IR spectroscopy also. Okay, so that was the part I intended to discuss before dive into today's discussion. Anyway, so these are the things I already cleared, right? That you will get this video and all. So today we are going to focus on this infrared spectroscopy, that is your vibrational spectroscopy. And why do we study infrared spectroscopy? Because from here we will have the idea of a bond strength. And from so this infrared spectroscopy, what we are going to study the physical chemistry perspective, right? Obviously organic chemists use these, organic or inorganic chemists use this process as a characterization technique to their molecules, right? Because the molecules have some fingerprint region where a specific functional group will appear at certain region, so that from there one can conclude that this bond is there. Suppose hydroxyl bond appears something around 3600 centimeter in, or something like that, 3300, I am not sure about the exact location, but it is a broad band. Then your NH bond or CH stretching, those things come into the place. But our main focus will be in the physical chemistry perspective. First of all, infrared. When we discuss infrared, now infrared in wavelength scale, it is more than the visible region. So visible region is from something around 350 to 750, suppose 800 nanometer. Now after that it starts infrared. Maybe in spectroscopic term, if you do some fluorescence spectroscopy or something like that, you will heard the term NIR emission, near infrared emission. So that comes, why it is called near infrared? Because it is near to the visible region. So then near infrared and then far infrared, these kind of things are there. Okay, that thing is clear. And obviously, we are discussing now infrared spectroscopy. Earlier, we have discussed rotational spectroscopy. So as you can see that your frequency is much higher for infrared spectroscopy, which also tells us that we are dealing with higher energy levels than the microwave spectroscopy. And that we are going to discuss after some time. First, let us start with the week 1 and week 2 assignment problems. So these are very easy problems. What we have already discussed the numericals also, right?
Yeah.
First, there is a example of a quantum field calculation. So did you get the correct answer for this?
So there is a mismatch between the. I hope that I got the result 0.2785, but
Okay,
the answer that you provided in the solution, that was point between 0.21 to 0.26. There is
0.21 to 0.26, and you got how much?
a 0.2785
Oh,
means 0.28.
let us calculate. Then I don't have the exact value right now, but let us calculate together. So we already know the formula, right? So this is for the sample. If this is for sample, then so this is through the relative method, and this is for the standard, right? The quantum field of the standard. Then we will have the total intensity, means the total photon counts or total emitted photon counts, that will come from the sum of the or integrated fluorescence spectra. So that, first let me write it phi sample. I will write it phi sample. Should write once. This is the reference. Then I of reference. Then we have the absorbance correction term, and that will appear something like this. This 1 to the power 10 to the power minus absorbance of reference, 1 minus 10 to the power minus absorbance of sample. And then we have the solvent refractive index. So this is for sample. Sample means sample is dissolved in some solvent. So sample means not for the sample. Sample in some solvent. Suppose it is water, then it is 1.33. Okay, something like that. N square reference. Reference in some solvent. So I think for this particular question, the solvents, I think they are taking maybe same sample, same solvent. So I can erase this part, right? So I'll not think about this, and let me put the values, other values in maybe some different color. So phi f is given, right? This is 0.25.
Yes.
And now intensity of the sample is also given 5000 units, and same it is 2500 for the reference. But there is a difference in the uh, uh, I should say the absorbance value. So it is something around 0.25 for the no 0.25 for the reference. Oh, no, 0.10 for the reference and 0.20 for your sample. Now, one thing to remember for quantum yield, so see, this is a numerical problem. But what I am trying to give you from a researcher perspective, whenever you are going to measure a quantum yield, na, don't go. So don't keep absorbance at your excitation wavelength over zero point 0.1. Even better if you keep it 0.05, something like that. Okay. Uh,
Yes. Yes.
Else some inner filter effect, those kind of things may come into place. You never know. If your sample is highly emissive, then that is one of the problem I have seen, I have faced. And one more thing, choosing your appropriate standard quantum yield. So it doesn't depend whether your emission maxima matches or not, but there should be a significant overlap between your absorbance spectra of your sample that with your reference. Okay, it doesn't matter if the emission matches or not, but the excitation spectra should have a good overlap so that you can choose a particular point where you want to excite your sample. Even you can excite your sample at your sample maxima, absorbance maxima. I'm digressing a little bit. Let us solve this. So first of all, we can see this will come as 2, then this. Acha, I can't cut this. Acha, one more thing. If the value was less than 0.04 of the excitation, I could have directly written as 0.04 and 0.02, something like that here. Means from 1 so I could have written 1 minus 10 to the power minus 0.04 or 02 as directly as 0.02. But it has quite some value, 0.1 and 0.2. So I have to do it. I have to use the calculator and get the value. So it will come something like 0.5 into 1 minus 10 to the power minus 0.1 divided by 1 minus 10 to the power minus 0.2. Let me use my calculator. If the value is given wrong in the your assignment answer, I'll contact them and ask them to change it so that maybe your marks from the evaluation should not get cut due to that. I am also getting something like 0.278,
Yes. Yes.
or
That's
I
the
should
value I
say
got.
0.28. So if
Yes, yes.
anyone other than Shoumitru is there, they did they also get 0.28 or something else?
The Suman Paja was there. He was also getting the same value.
Okay, so 0.28 should be the right answer. So I will contact them. 28 or 27 means, see, this can.
2785 the exact value I got
So
while calling.
I'll ask them to keep the value between 0.25 to 0.30, right? Actually, I think what they have done, what I can understand, what they have did is that instead of 1 minus 10 to the power minus 10 to the power minus 0.1, they have directly written that 0.1. I guess by that they are getting something like 0.25. Okay.
Okay.
And that's why what was the answer given?
The answer they provided that was in between 0.21 to 0.26.
Okay, that's why you got my point. If you directly take that 0.1 and this 0.2, then a two factor will come in the denominator, which will cut with this, and it will become 0.25. Maybe that's what the other. So that's what mistake they have done. They cannot do this. As you can clearly see, there is a. I would say there is a significant, and this is going to be a significant error. But see, if the absorbance value was less, then we could have done that below 0.04, something like that. Okay, if the
Then
absorbance
only we
value,
can do Taylor expansion. We can do, sir.
yes, 10 to the power minus 0.04 would have become uh, 0.04. 1 minus 0.04.
Yes, yes.
Yes. Okay. Now the next question, let us go for a Michelson interferometer. The velocity of the moving mirror is given. So that is Vm is equal to 2 meter second inverse. The signal on the interferometer of the, so the wave number is given. Okay. So wave number means 1 by lambda, right? Or nu bar. So that is given 1000 centimeter inverse. Okay. Now what we remember that for a constructive interference, what we will require is that your, if the speed of your Michelson moving mirror is Vm and it is moving for tau time, then the distance cover is something like la- lambda m by 2 for a constructive interference, right? For to get a signal, means for a peak to peak distance. What I'm trying to say. Do you remember that? Or
Yes, yes.
okay, okay. And we need to move the mirror by lambda m by 2 so that the now the light will move lambda m, because if we move it lambda m by 2, then light has to cross that path twice, right? It will once come and then it will go.
Yes,
Sorry for the so please hold for a minute, I have to take a call. It would be 30 seconds.
yes, yes.
I'm teaching, I'll call you later. Thank you. Yeah. Okay. Okay. So now Vm is given. Tau will relate to the frequency, right? Frequency is 1 by tau. So this is the frequency of your um, movement of the mirror, or for the instrument, I would say, right? And this lambda m has the information from the uh, frequency of your source, light source. So that's how actually using this Michelson interferometer, what we do, we modulate the frequency. So from tau, we will have the information from the instrument uh, frequency, and lambda m by 2 is related to the light source frequency. Because the lambda m is, let me, 1 by lambda m, or why I'm writing lambda m, I can write lambda, right? I was writing Vm, that's why I guess. So this information is already given. So let me get tau. tau will be lambda by 2 Vm, and I need to require the frequency. So maybe same lambda by 2 Vm. So F is 2 Vm by lambda. So 1 by lambda is already given, that is 1000 centimeter inverse, and then 2 into Vm is 2 meter per second. So 2 meter would be 200 centimeter and second inverse, right? 2
Yes.
into 2 Vm by lambda. So it would be something like 4
4 into 10 to
into
the
10 to the
5
5 second inverse, right? Yes. So
March. Yes.
that is Hertz. So it would X would be Hertz. So 4 is 4 into 10 to the 5. So there could be confusion, like suppose someone may say, why aren't you writing it 10 to the 6? It could be zero point 0.4 into 10 to the 6. But see, that time we have to go with the significance value, right? Significant number. So it is zero point 0.4 into 10 to the 6. So it's not, zero point 0.4 is not 1. It is close to 0. So by that way, we are telling X is 5. Maybe I think for the answer, I don't think they have a particularly 5, or they had some range. Do you remember if they have given a range or something like that, that
They
one can
provided 4 to 6.
4 to 6? Then it's great. Then so it's fine. Okay. Now give me the answer of this. Unit of absorbance.
Unitless quantity.
Unitless quantity. Please remember this. There are many literature in the means there are many papers in the literature. They give absorbance as absorbance unit, or I don't know, arbitrary unit. So the basic practice is that for fluorescence we write arbitrary unit, because it is something like for a correction factor or something is multiplied with the exact signal. I told you, right, that the emission spectra we record in a spectrophotometer, so that should be what I should say. Suppose I have a coumarin or rhodamine or some molecule. I have a emission spectra. So I will think that if I am using any other spectrophotometer, or someone else, some other researcher is doing research on their lab in some foreign country, they have some different spectrophotometer. So the expectation would be that the emission spectra should look same, right? Or the quantum yield should be similar. But the problem is every instrument comes with a, separate problem. I will not say problems, their own limitation.
Intrinsic property. Intrinsic property.
Yes, because that we, I think while discussing the monochromator and detector, we told you that there is some correction factor is associated. If you, so for individual instrument, you will have a separate correction factor associated to that instrument. So when you apply it, then universally your spectrum is corrected. So whatever you are getting here, you should expect the same spectra to be replicated on other instrument also. Not, I am not saying in terms of intensity, but what I'm trying to say, when you normalize it, it should look the same, right? The FWHM of the spectra or the spectral maxima, that should come at a same portion. So for that, what we do, that it's not really, so whenever we multiply with that correction factor, it becomes something like CPS, counts per second, divided by some uh, something, some unit in micro ampere, something like that. I am not getting into the details, but the whatever I'm trying to say is that we use arbitrary unit for fluorescence spectroscopy. So, so sometimes what means by when they close their brain in during the absorption spectroscopy, someone also write absorbance, but in bracket they write arbitrary unit. But we have to be very careful, we should not do that kind of mistake. Anyway, uh, question number 4: speed of a moving mirror in Michelson interferometer determines what?
Resolution of the measure.
A resolution of the monogon. It doesn't get the range of wavelengths, right? It doesn't. The range of wavelength is not the correct answer, right? because
Yes,
you
yes.
can you can all the thing will come into this yeah, your time domain spectra, right? All the wavelengths or frequency are recorded at the same time, and then when you do the Fourier transformation you will get some the result. Okay, that's good. Then question number 5, resolution of a scanning frequency domain absorption spectrum depends on. So this means the frequency domain means the normal spectrophotometer.
Yes.
What does it depends on?
Now, it also resolution also depends on your detector also. Let's say you are using, let's say, HPG detector, or you are using, let's say, something PMT like of detector.
Hmm.
Then your resolution will be better in the case of like this HPG kind of detector.
So that is actually your what you are trying to say. HPPD or those kind of detector will give you resolution in time domain. So here, what they are asking is the frequency domain. So that
Yes.
means in the wavelength scale.
Yes. In the this frequency domain also, let's say we have two peaks that are very closely spaced.
Okay.
Okay. So if your detector is have very good resolution, it also detects, depends on your detector. Let's say you are using your PMT kind of detector, or let's say one is using high purity germanium kind of detector. Let's say
Okay.
it can be anything. Let's say sodium iodide detector, or one is using HPG kind of detector. In that case, your resolution will be better in the case of HPG detector. I think so.
Okay. Okay. But
Uh,
for this
uh,
specific, yes, yes, please.
am I able to clear this thing?
So
It may depends upon detector also.
it goes that will again comes to the detector. So the quality of grating or detector, that is also coming to the monochromator, right? How many for now, I mean, the monochromator and detector are two separate units, obviously. The quality, when we discuss the grating and slit width, we are discussing about the monochromator, emission monochromator, or the excitation monochromator, obviously. Detector will also play a role, to be honest. um, I think you are correct, but I need to discuss these ones. Detector, yeah. Suppose you have a SPAD kind of a detector where the active area is very less. So, but think of it like resolution of a scanning frequency means you have to decide on the change in the lambda. So
Yes.
first of all, we are in the same page, right? That slit width and quality of the grating will have
Yes.
a role to play. In
Yes.
intensity doesn't matter, right?
Yes.
So intensity actually matters when we are discussing signal to noise ratio, right? That
Mhm.
time it will matter.
That
Now,
also contributes to the resolution also. If your signal to noise ratio is good,
so that time your
then
signal will look good.
yes.
That time your signal will look good. But so to get if the question was something like that, if what are the things you require to get a very good looking spectra, good looking signal, I would say,
Mhm.
then intensity of incident light means what will depends on the signal to noise ratio, that came into the picture. But for the detector, so how are you defining? Means can you repeat? How do you think that the resolution in the wavelength scale will be dependent on the detector?
In the case of slit width, you are just selecting only one wavelength at a time.
Hmm.
Okay. By adjusting slit width, you are just passing only one wavelength at a time. And if you broad the slit width, then maybe two wavelength can pass through this.
Yes, right. So that's why you are
Yes.
losing your resolution,
Resolution,
right?
yes. In similar way, as I am working in this BRC, we have
Okay.
let's say gamma detector, gamma spectrometry is carried out using sodium iodide detector. It is a
Okay.
scintillation based detector, and the
Okay.
another detector is like, let's say, HPG, high purity germanium based detector. Okay.
Okay.
So in this case, if you are able to see the two spectrum, then you can see in the case of HPG, more number of charged particle is created, because the
Okay.
band gap is lesser. If more number of charged particle is created, then the resolution obviously will be better. So you can see the in the case of HPG detector, the resolution is better compared to sodium iodide detector. Means you
Okay.
have multiple number of, let's say, multiple number of peaks are there. Then you will
Hmm.
obvious your obvious choice will be HPG detector. But there
Okay.
it will comes with certain limitation. You have to cool it using this uh,
Liquid nitrogen or
nitrogen.
Peltier
Yes,
effect.
yes,
Yes.
yes, yes,
Okay.
yes, yes.
Yes. Okay. Okay. Maybe that's one point I should also take into account. Okay, that's good. Maybe then we can write this for now. I'll discuss with professor if we can give a marks on this. But your point is well taken. Okay. Now question number 6. Quantum yield of a sample recorded using a fluorometer will depend on what?
Sample only.
Sample only, right? Because all the other parameters for your like, so mostly when we are discussing quantum field, there are two processes. Did I discuss two processes, or only we have discussed only using the relative method, right? The another process is known as absolute method. So the absolute quantum yield for that is required for the mostly related to the solid state quantum yield, or you want to record for a thin film or something like that. Then you want to do you want to have a integrating sphere, something called as the integrating sphere, which is uh, it's not a black box but a white box, something like that. Inside the integrating sphere, it is coated with barium sulfate powder, white. So means you excite your sample will be at some point, if it is solid sample, even for a solution sample also you can record a absolute quantum rate, but that is recorded using an integrating sphere. So for that, what actually happens is that, suppose for an integrating sphere, what we record is that, so suppose your sample, so when we generally record a emission spectrum, suppose my emission excitation is at 300 nanometer, lambda excitation, and emission ranges from 320 nanometer, suppose 400 nanometer, just arbitrary. So generally, when we do record a emission spectrum, we try to avoid the first order and the second order diffraction. Okay, and record something like this. Suppose this is my emission spectrum. Okay, which, so suppose this is my 400 nanometer, and this is suppose start from my 320 nanometer. This is lambda scale, and this is obviously intensity. But when we use this integrating sphere to record the quantum yield, absolute quantum yield, that time what we measure is that we also want to measure the first order diffraction peak. So if I am exciting my sample at 300 nanometer, then I start, the range is something like 290 to end of the spectrum. Okay, so we try to record the whole first order peak, something like this, huh? And also your emission spectrum, something like this will come. And next, what we do, suppose this is my sample, and then I take a reference, not a reference, but a blank sample. Suppose, sorry, you are recording some solid samples. Now you record some purely white sample, something like barium sulfate or whatever material is used in your integrating sphere, which doesn't have any emission. So for that, also you record the, obviously you have to record with the same parameters, and that will, I guess, come something like this. I should use a different color. And let me know if you already knew this, so I will not discuss in depth. This is just for
No,
your
I
information.
don't know this first
Okay.
time.
Okay, so this is something you do for a your blank sample. Your blank sample will only have this first order diffraction peak. It is not emissive, right? So you will get something like this. So from here, what exactly information we get is that, see, again, same as the EA method. So we break. this spectra into two parts. One this, one of your emission, and another is for your this diffraction peak. So from here, whatever area under the curve is there. Okay. So what we know of the quantum yield? Quantum yield is pi f is number of photons emitted divided by number of photon absorbed. So see, so from the fast order peak, actually, what gives us the idea from the scattering peak? What we get the idea uh, intensity of your excitation light. Okay. Now, when there is no sample or fluorescent sample, then you are getting something like this red, uh, this whole red thing, right? This is your uh, number of photon that is possible, means that is coming from your excitation source. And when you are recording for your sample, then you are getting a different this area, right? A little less than what was there when there was no fluorophore. So the red area minus the blue area is going to be your number of photon absorbed. Okay, this part is going to be your denominator. This red minus blue, I would say. The area under the curve. Area under the curve of a spectrum will give you the information about the number of photons. Okay,
Yes,
total number of photon. So red minus blue from the first order diffraction, this peak will give you number of photon absorbed, and from here you will get blue minus red. So that is going to give you the photon emitted. Okay. So that's how you calculate the absolute quantum field. In this case, you don't require a reference sample. Okay. Uh, but uh, but for this method, actually for any spectroscopic method, you have to be very careful, and you have to reproduce this result. Sometimes what happens that people just do it for the sake of doing it, and the result doesn't reproducible, the absolute quantum field. So one have to be very careful. But that depends on the how good experiment can be done. Anyway, let us not digress anymore. We are getting information, but maybe we don't want that much. Anyway, so quantum field of a sample, yeah, recorded using a fluorometer going to depends on the sample itself. Okay. Now let's go ahead. Question number 7. This is I think a good question. Good question because again, a sample is a mixture of two compounds A and B, which absorb light of wavelength 400 nanometer and 600 nanometer, respectively. Okay. So one inherent approximation would be that no, the approximation doesn't hold here. Anyway, so I was going to say that the A doesn't absorb 600 nanometer and B doesn't absorb 400 nanometer, but that doesn't have to be the case here. Anyway, um, respectively, the ratio of absorbance at these two wavelengths for the mixture is 1:4. Okay, let me draw it. So this is lambda, this is going to be 400, and this is going to be 600. And this is absorbance. Absorbance is also known as OD value. So that is your optical density, same as absorbance. Sorry. So absorbance, ratio of the absorbance at this wavelength is 1:4. So this is for the mixture. So A absorb at 400 and B absorbed at 600. So we have to now mixture of the concentration. Concentration of A is thrice that of B. So first of all, absorbance of A, there is a something called Beer-Lambert law. Can you recall what is the Beer-Lambert law?
Epsilon CL.
Epsilon Cl. So
Yes.
is epsilon dependent on lambda?
Epsilon dependent on lambda.
Mm,
Yes.
does it depend?
Of course, it may. Of course, it depends.
It actually does. Then what about C? Concentration,
It's
does
the
it depend?
concentration. It's the concentration basically.
So it doesn't depend, right? And L, does it depend?
No, it's the length of the sample through is
Uh,
the light or this EM.
Not the sample, but the sample holder, or you can say
Yes,
cuvette.
yes, yes, yes.
So this is
Incubate.
going to same for both, right? So okay. Now what about the B? Epsilon B also will depend on the lambda concentration of B and L. Now what they are saying, if I take a ratio of this, A of B, absorbance of B by absorbance of A, then I am going to get epsilon B at lambda into concentration of B, then epsilon of A and concentration of A. LL got cancelled because we are doing it in the same uh, instrument, right? So path length is same, not instrument but same cuvette or something like that. So there is a difference between the absorbance is given 4 by 1, right? Uh, Epsilon B by epsilon A is not given. Uh, and what else is given?
Concentration
Um,
ratio is given.
Concentration. Concentration is A is thrice, so 3C, and B is C. So C gone 1 by 3. So epsilon B is 12 time of epsilon A. So what information does it? So ratio of their absorbance coefficients or molar absorption coefficients, right? So that is 1 is to x. So they would write epsilon A by epsilon B. That would be 1 over 12, right? Epsilon
Yes.
A by epsilon B 1 over 12. So it is going to be 12. So from here we get the idea that your molar absorbance coefficient of B is much higher than that of A, because even if the concentration is higher of A, still the absorbance is higher for B, 12 times. Anyway, that part I think is clear. Now let us go to, I think, the first problem of the assignment 2. Periodic boundary condition used for a dependent part. Used for the dependent part. I think they wanted to say phi dependent part, I guess. Let me write it here maybe. Periodic boundary condition used for phi dependent part of the Schrodinger equation for a rigid rotor builds upon on the requirement of wave function to be
Single value.
single value. Now second, spacing between the successive uh, microwave spectral lines are
Same.
same, that is 2b, right?
Yes.
Yes. Lowest allowed energy is 0 for,
Rigid rotor.
and how does it possible? I think you only have given the
Equal to
answer, right?
0. J
Yes.
equal to.
No, j equals to 0, but I am saying that how
There is an infinite possibility of the
the
position.
position, right?
And phi.
Because theta and phi. Yes, right. Now, microwave spectrum of a molecule in absence of any external electric or magnetic field can be used to determine
Is micro bond length.
bond length. And what will happen if there is an external electric or magnetic field? What will happen?
Then dipole moment.
No. Then what will happen that your that state, suppose uh, j equals to 1, that state in absence of a magnetic field, how many states are related? What is the degeneracy of J? J equals to one state.
Yeah. J
Hmm?
equal to 1
Yes, J equals to
only.
one. So what is the degeneracy of this state, rotational state?
Only one degeneracy.
No, degeneracy is 2J plus 1
Okay, okay.
because AM states are AM number of states are there in J. Now AM is 2J plus 1 means there are 2J plus 1 number of states. It depends on the yeah, your Z Z yeah,
Yeah.
orbital
Values of Z.
Z coefficient Z coefficient I am saying. So your
Z component of the J
yes, the
wave.
component of the angular momentum, right? It depends on the magnetic field. So how does it orient into the space? So it will be something like 2j plus 1 in presence of the electric or magnetic field. So j equals to 1 will not be degenerate. So the three state will have three difference theta or phi values, right? Anyway, so that time your I think your spectra will also get divided. I think that your then it will be hard to get the 2b value or the spacing between the points, and that's why then determination of the bond length won't be that easy. Anyway, I hope you got the message what I am trying to
What
deliver now.
then? What extra information it will provide if there is some external electric or magnetic field is there? What extra information it will provide if there is external or magnetic field is there?
Means you will get the idea about the for a particular molecule maybe you will get the idea of the z component of the orbital angular momentum, the value of that you will get an idea for individual states, but I'm not sure how experimentally you have when you will record the energy gap then you will have that idea from means from the spectra. Your spectra will be splitted, right? That time means from one spectra it will be so whatever you are recording as a spectra that is a gap between the uh, so 2b, 4b, 8b, something like that,
Mm.
right? Now it
Yes.
will I think split. It will split into different uh, energy levels. So one will be, suppose previously one would be 2b and now one will become so one state. If it was like in absence of magnetic field, the energy was something like that. For j equals to 1, it will split into these three. So your spectrum will split into three. Then I think it will not be easier to determine. So that time it will be hard to determine the bond length because that the gap between the successive lines, I don't think then it will be 2b something like that. I'm not sure about that, but you will have obviously you are going to have an idea about your z component of the angular orbital moment, right? It
Okay.
is something like what L or M. So it is going to be M H cross, right? Your Z component. So it will be plus H 0 and minus 1, something like that.
Okay.
Okay. But what I'm trying to say experimentally, I think you are going to see splitted your spectra, whatever was there, that will split into three spectra. Okay.
Yes.
Because will it split into two or it will split into three? That I have to check. It depends on the then another prospect of that delta M will come into the picture. So there are something in the selection rule that something delta M was there, right?
Yes. Yes.
So that
That
will
time.
also come. So that will also come into the picture. What is the delta M value? I guess so. I'm not sure. I'm not sure at this point of time. I have to look at it. But I think that will also come into the picture. Okay. Whenever you are looking at the transition. Okay, let us go to the next question. Maybe the spacing between the rotational line is HF is 40 centimeter inverse. That means your 2B is 40 centimeters. Your B is 20 centimeter inverse. So
Yes.
corresponding spacing between the rotational line in DF is, so we are not going to calculate this because we have already done some significant number of numerical problems. So we'll get the B value, right? The rotational constant. But the
Yes.
rotational constant is also dependent on what are the factors?
This mu basically reduced
Mu.
mass.
Right. The in the ambit of the assumption that the length is going to be the same. So just here the mu reduced mass is going to change. Will it is it going to increase or decrease for DF?
This reduced mass will be it will be decreased.
Is it so?
Uh, uh,
So for
but
this it is 1 into 19 by 20
yes,
A mu,
yes.
mu for HF and mu for DF 2 into 19
Reduced mass will increase.
increase,
Reduced
right?
mass
That's yes, that is what I was trying to say. It is going to be more
will
than one.
definitely. Yes, yes,
Ha,
will definitely.
so if mu df is increase, sorry, if mu df, if the reduced mass is increasing, then what will happen to the rotational constant?
V will decrease.
B will decrease. So B will decrease means earlier B was 20 centimeter inverse. Now it is going to be less than that, right? So, so see, we don't have to even calculate from the option itself. You can see there is only one option which is less than 20 centimeter inverse,
Yes.
which is 7.9 centimeter inverse. So that's great actually. So I thought I will not calculate, but anyway, we got the answer. I hope that is the correct answer.
Its answer will be 20 centimeter inverse because
Uh,
you have to. Its answer will be 20 centimeter inverse.
20.
Yes, because we have to calculate 2b value, only 2b. The spacing between rotational line in the case of this HAB is 2b. 2b is equal to 40 centimeter inverse, and they are
Yeah,
now
okay,
assuming
okay, okay,
40.
okay, 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 okay. Right, right. You are correct. So actually, I was thinking about the B values only. Okay,
Yes,
sure, sure, sure. Okay, so the answer is going to be B, right? A 20 centimeter inverse, you're saying means
20
it
centimeter.
is coming to be the B is coming to be 10 centimeter inverse.
Yes.
Okay, 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 good, good. I actually I haven't checked the values. I was just going through the assignment problems and take a screenshot of this and discussing here. Anyway, okay, I think we don't. Acha, we have some problems here. Spacing between the successive energy levels of a rigid rotor is same. What we just discussed 2B. Why the same question is coming again and again? Anyway, out of the following molecules, microwave activity is observed for the polar molecules, right? HCl and chloroform. SF6 will have octahedral geometry, right? So eventually, its dipole moments cancel each other for each SF bond. So it is non-polar. Anyway, now fast rotational absorption of 12CO occur at this thing, rotational absorption fast. So what do you think? This talks about the energy or energy difference?
Fast rotational absorption. Their absorption means they are J into J plus 1 means they are no rotational absorption. No, I think
That,
2b is 2b means they are talking about spectral lines.
yes, that is actually to be. Why? Because it is epsilon, I think, um, 1 0 to 1.
Yes, yes, 0 to 1. Yes,
So that would be what was the formula? 2b j into j plus 1, j is 0.
2b only 2b.
So so it is 2b. That's why it is 2b. It's not 2b because of the spectral lines. So one
Yes,
have to be remember because if it is given second rotational absorption or third rotational absorption, then it would have been different, right?
yes,
Okay. So 2b is something given. So anyway, we are going to get b value, and then again it depends on the reduced mass, right?
yes.
So we are not sure of the reduced mass because we are not sure which isotope of carbon is used. So it would be something like 16x divided by 16 plus x, and from here it is 12 into 16 divided by 12 plus 16, which is 28, right?
13. Yes,
Uh, yes. So this is a in AMU. We don't have to go to. So
Yes.
when we will discuss in some ratio, so that time we don't bother about the we have to we can keep them same. Now, so from here we yes
Sir,
yes
for question number six, the answer will be B. Means
B.
the spacing between successive energy levels of rigid rotor increases with increase in energy. It is J
Yes,
into
yes,
J plus
yes, yes. Sorry. Right. So actually, it looks like this, right? Suppose I say this is my. I am discussing this because you have already learned the vibrational levels about something about that. Now it actually contains the rotational lines, and they actually increase in energy, right?
yes.
Like this. So this is actually your J9, 950. Yes. J dash is equal to 0 J dash for this. Now this one, 2, 3, 4, and they will increase. Right? You are correct. You are correct. It is all because 2b into j plus 1. If j is increasing, then it is increasing. Okay.
Yes.
Thank you. Thank you for correcting. Uh, for here, you already got the 2b value. So it is something like 2b by 2b dash is equal to 3.8424 divided by 3.6734, and then you can directly replace your b with b or b dash with your reduced mass because other things are same, right? So as they are inversely proportional, so it is something like mu dash divided by mu will come. Then it is 16x divided by 16 plus x divided by 16 into 12 divided by 28. 16 gone. Then
And
12
X
into
becomes 13.
x will
X is
become
equal to
is
13.
going to be 13. Okay, thank you. So x is going to be 13. So 13c. Obviously, there are 12 and 13c is there. Anyway,
Yes.
yes. Okay. Uh, so definitely it is not going to be 12.
Yes. Yes.
Yeah. So let's go ahead. Uh, okay, I think I have kept this white space for discussing the formulas regarding the IR spectroscopy. How much time do we have? We have 1 hour. Okay, so I will not go into the deep of the I am not going into the selection rule or the Hermite polynomials and all. You have already learned it from the lectures, right? So we are basically going to deal with this equation. The energy of a vibrational state is going to be V plus half into H nu V in centimeter inverse, right? Or this is not in centimeter inverse. For centimeter inverse, it has to be nu
Bar.
bar, and H I think would not be there.
Yes.
For from joule to centimeter inverse, you need to divided it with HC. So your H term also got okay, and your C will come here. So it will become nu bar. So this is new vibrational, and one thing we are discussing. Sim. Sorry for this. So we are discussing simple harmonic oscillator. So this is the energy is going to be associated something like that. How does the wave function looks like? There is going to be one normalization constant. Then there is going to be what one exponential term, right? Exponential of what was there minus alpha x square by what? Let me check on alpha x square by 2, I guess.
X square by 2.
x square by 2, and some Hermite polynomial, right?
Yes.
Dependent on the not x but root over alpha x, and alpha is given by something like alpha is also dependent on your force constant. So, and similarly here the reduced mass is going to be there, mu r reduced mass, and your Planck constant, reduced Planck constant. So this is something that your harmonic oscillator, wave function of a harmonic oscillator will look like. You know the potential energy, that is plus kx square. The k is your force constant, right? So I am trying to write down the equation what we are going to use for solving the upcoming numerical problems. Force constant, and how does this new wave, so when it is only frequency, how does it related to the force constant? Do you remember?
Power of k by mu.
1 by 2 pi
Yes, power of k by mu.
k by mu. And if it is nu bar v in terms of wave number, then 1 by 2 pi c will come, right? K by mu. K by mu or m. Uh, Here it is mu because we are discussing a two body problem, and we have
Yes.
converted that two body problem into a one body problem where we are, that's why we are discussing reduced mass. If it is one problem we are going to discuss where it is something going to be a single body, means altogether it was a mass, some physics problem. Okay, I am not going into deep onto it. What are the selection rule? We have the selection rule delta v equals to plus minus 1. What else have we learned from here? We have learned the so how it can become a, how one molecule can become IR active. What are the so this is a selection rule delta
There,
v equals to plus minus 1. What are the other conditions?
there must be a change in dipole moment.
What about uh, permanent dipole moment? Is there
There,
any
it is not
requirement?
required, but there must be a change in dipole moment while this
Transition
oscillating.
takes place. Transition takes place. Right?
Yes.
Okay, good. While oscillation, there should be some change in the dipole moment, and that is going to be also constant in ambit of simple harmonic oscillation, right? Then it is going to be constant, some d mu by dx at equilibrium distance, x is equal to 0. Here x is your uh, means how much you are uh, how far it is from the equilibrium. It is not really the Cartesian coordinate, it is how far it is from the equilibrium, the x. So from here we will get the selection rule. I'm not going to that. And then professor has discussed about the row vibrational spectra, right? Row vibrational spectra, we have discussed two conditions. One, when the Born-Oppenheimer approximation holds, like the B is same. So I think we have discussed a problem similar to this in the earlier assignment, not assignment, but earlier the previous session, where your in excited state your rotational constant got changed, right? So we have discussed a problem similar to this. Anyway, so in that cases, in Born Oppenheimer approximation holds, that will give us one kind of spectrum or the spectral energy, and another will come where the Born Oppenheimer approximation breakdown of the Born Oppenheimer approximation, and which is actually is the uh, I would say, see, uh, non-rigid rotor or this simple harmonic oscillator, these are the approximate system what we are working with, right? But the real vibrational thing, those things that are not, that may not be that simple, right? It could be so anharmonicity is there. or I would say that your Born Oppenheimer approximation may not hold, right? And that is actually the real case. So that time you are going to get a different expression for the your transitional energy, right? And then professor has discussed the anharmonic oscillator, which is when your oscillation is more than means actually that is the real condition. So in case of SHO, your potential energy PE or V, I would say, half kx square. So that follows I would say a parabola, right? A symmetrical parabola. But in case of an harmonic oscillator, you are going to see something like a Morse potential, which is known as a Morse potential. And in case of a SHO, the the concept of dissociation energy was not there. But here you would say that your vibrational lines. So what actually happens to vibrational lines in case of rotational energy with increase in rotational number, your spectral difference is going to increase, right? But in case of your vibrational spectra, you are going to see the opposite thing due to your anharmonicity constant. I will show
Uh,
what I'm trying to say. So in case of so how does it relate? Your new energy for anharmonicity when it is involved, it have V plus half new V minus new plus half square of that. Then your anharmonicity constant is there, and another term is there, that is your new V. Okay, and
yes.
this anharmonicity constant is also related to your dissociation energy by some formula, your V dash V bar for dissociation energy. So, so for a rotational, for a simple harmonic oscillator, if suppose if a MCQ type question comes, what is the anharmonicity constant for a, or what is the dissociation energy will be for a say, when you discuss you when you approximate it to be a simple harmonic oscillator, what is the dissociation energy?
Dissociation energy is I have to calculate the D value. D
Calculate,
zero
calculate.
value.
Huh?
I have to calculate from the most potential.
No, I am giving you this equation, na.
Okay.
So what is XC?
Enharmonic.
So for a harmonic oscillator, what would be the value of XC? Hmm? It would be zero, right?
Okay, for harmonic oscillator. Okay. Yes, yes.
And this is how it looks like. So there is no dissociation energy, or I would say the dissociation energy is infinity
Yes.
when we are discussing a simple harmonic oscillator.
Yes.
And when we are discussing this, when the anharmonicity comes into the picture, then it is related to some dissociation energy would be there.
Yes.
Okay, just wait for a minute. Okay, so that part is done. Now, uh, what would be the selection rule for this? For
Can
when
be
the
any value.
anharmonicity is there, then the selection rule become not only plus minus one was there. Now
Uh,
it would also become plus minus two, plus minus three, and so on. But one more thing that I have not discussed yet, that what is the most populated state for a rotational, when we discuss the rotational spectra, What are the things? It depends on the population.
Population, I do not understand your question.
So
Means it can take any values because the room temperature it can take any values, but the means j equal to 1 is possible, j equal to 2, 0, 1, 2, all these values are possible.
yes,
But
but but
in the case of vibrational, only v equal to 0 is only possible
right. And
at
one
room
more thing,
temperature.
why I invoke the that rotational spectra population of a rotational state, because if you remember that that rotational spectra, there is also the degeneracy will also comes into the picture along with the your Boltzmann distribution function, right?
Yes,
So
yes, 2z plus 1 is there.
yes, so they are there to and for a vibrational level, is there any degeneracy associated?
No, there is
There
no
is none.
degeneration.
There is none, right?
But but I have
Yeah.
a doubt. If we are not talking about the spin kind of thing, if spin is there, then you
Mhm.
have this degeneracy will come now.
The spin comes from that electronic. Um, I would say that would be related to the spin, right? Yeah, electronic states.
Yes,
Would it?
electron spin or this molecule also has some spin. Total spin will be there.
But we are in ambit of yeah, Born Oppenheimer approximation. Whenever this question comes, take a easier route that that time I say that we are in ambit of Born Oppenheimer
Yes, yes, yes.
approximation and
Because
those.
I'm from physics background. That's why I'm
Okay,
asking this question.
okay. So I'm not sure about that. I think we cannot discuss we cannot relate the spin with the vibrations. I'm not sure. I'm not sure at this point of time. I've not thought of it.
Okay, okay.
So okay.
But in
So
statistical mechanics, they consider all these things. They consider also spin. Also, they consider.
yes, perhaps, yes. Okay. Okay. Yeah, so what I was trying to say that before you have already given the answer that the most populated vibronic state would be V equals to zero, right? And from there, most of the transition is going to take place because earlier when we are in ambit of simple harmonic oscillator, then it was V equals to or delta V equals to plus minus one. So mostly the we are discussing about or the transition we were able to see was from V equals to 0 to 1, and professor has shown us some yeah, vibrational spectra of HCl, right, where we have seen that P band and R band, right?
Yeah.
The
Yes.
P band was something like, I guess, V equals to delta V equals to plus 1, and delta V equals to minus 1 was R band, right?
Yes. Yes.
Yes. So, and one more thing, we did not see any band in actual. So, uh, we are not going to see any band in at this wave number. We are going to see something like plus minus 2. What was that? 2b something like. Let me remember. Let me look at the equation. 2j plus 1, I guess. 2b into j plus 1. So so the plus is going to give us, I guess, the R band, and minus is going to give us the P band. So uh, the higher energy band was R band, and lower energy band is P band, something like that.
Yes.
And when the anharmonicity comes into the picture, then not only these vehicles to 0 to 1 transition is possible, that time 0 to 2, 0 to 3, these are also possible. And this is known as the plus minus 1 is known as fundamental overtone, plus minus
Yes.
2 is known as
Fast
the
overtone.
first overtone, plus minus 3 known as
Second
um,
overtone.
second overtone. Do you know something known as uh, hot bands?
No, I don't.
Okay, so there is something known as hot bands. You will get the idea from the Banwell also. Why? So hot band is the transition from vehicles to 1 to further levels. mostly V equals to 1 to V equals to uh, 2. Why it is known as hot band? Because when it is hot band means in presence of a very high temperature, then your population there is the some population will be there in your V equals to 1 state. Then you can see a transition from your fast excited vibrational state, that is V equals to 1, and you may observe a band there that time, and that's why it is known as a hot band. At higher temperature you will be able to see that. uh, Let me see from the band wheel if I can show it to you. uh, Infrared. And one more thing, during the SHO part, the energy gap were equal, right? H nu. But when it went to anharmonicity, the due to the anharmonicity constant, the higher we go, means the higher the value of V, the lesser was the gap, and ultimately it reached a continuum, and then just after that energy, the bond is going to dissociate, and then actually you are going to reach the continuum. See, I think here the so see the fundamental is from 0 to 1. 0 to 2 is with smaller intensity. Even smaller negligible intensity is going to be 0 to 3. That is your second overtone. And there is something. These three transition are shown in good approximation. And your obviously, and another thing, your anharmonicity constant is going to be very, very small. It is close to 0.01, something like that.
Okay.
And where is your hot band? I think I have read something here. Although we have ignored the transition from vehicles to 1 to higher state, we should note that if the temperature is raised or if the vibration has a particularly low frequency, then the population of vehicles to one state may become appreciable. Thus, at say 600 Kelvin, about 300 centigrade, population of vehicles to 1 divided by population of n vehicles to 0 become e to the power minus 2.4, about 0.09, and at room temperature it was something like 0.008. The transition from vehicles to 1 to vehicles to 2 will be some 10% intensity, those of the vehicles to 0 to vehicles to 1. Means this a similar increase in the population would arise if the vibrational frequency were 500 centimeter increase of, we may calculate, thus a weak absorption arise at slightly lower wave numbers than the fundamental, and such weak absorbance are usually called hot bands, since a higher temperature is one condition for their occurrence. So that is V equals to 1 to V equals to 2. So it may comes in a question something like that. So you should be you should know this. Okay, this may come. Okay, let us go back to the, now we can, I think we are ready to solve the numerical problems. Okay. First, some I think arbitrary questions are there. Which of the following molecules may show infrared absorbance spectra? Will H2 show?
H2 will not show.
It doesn't have a permanent dipole moment, and
Yes.
also when there is some oscillation, it is a linear diatomic molecule.
Yes. Yes.
So any change would lead to there would be no change in the dipole moment.
And yes.
So H2 is not it's not infrared active. What about
Yes.
HCl?
HCl has a permanent dipole moment, and if the pH change, it will also change.
It will also change, right?
Yes.
So uh, okay. What about CO2? Does it have a permanent dipole moment?
No, but there is a change during the vibration. The dipole moment will change.
Okay, so actually the question will come after some time, but can you tell me how many normal modes of vibrations are associated with CO2?
This for linear molecule 2n-1. I think 3n, 3n
3n 5.
3n
3n
3n-5.
5 for a linear molecule and 3n 6 for non-linear molecule.
Non-linear
And
molecule.
how does it how do we end up with that particular number? Because there are three. If there are n number of atoms in a molecule, then it is associated with x, y, z, three coordinates. So total number 3n is going to be the n number of atoms, 3n degrees of freedom, right? And now out of this, for a nonlinear molecule, suppose for a nonlinear and linear, nonlinear molecule, how many translational degrees of freedoms are there? X, Y, Z, right?
Yes.
So three. So for a linear molecule, how many translational degrees of freedom are there?
That is also 3.
Also three. How many rotational degrees of freedoms are there for nonlinear? It is actually two and three for this. Because I think the uh, uh, suppose it is rotating along x-axis, then your y and z are the sorry, I have written the different. It is three for the nonlinear and two for a linear. And that's why your so your vibrational degrees of freedom is going to be 3n minus 6 for the, so 3 will account for translational, 3 will account for rotational, so vibration is going to be 3n minus 6 and 3n minus 5 for a linear molecule. So that is your normal modes of vibration. What does it a normal modes of vibration means? Is there any abnormal modes of vibration possible?
Oh, it's possible, but they are in sync. Means they are in phase.
No, no, no. What actually I was trying to use a punchline anyway. What I was trying to say, why do they call normal modes of vibration?
Normal modes basically they are in phase. Means I think means all parts vibrates with same frequency and a phase. Means
No,
means
actually, why they actually call the normal modes of vibration? Because they are not actually dependent on each other. What I'm trying to say, they are not, or they are normal to each other. Means uh, by suppose there are, if there are 3n minus 6 number of normal modes of vibration, they are not related to each other, and you can get a vibration from a linear uh, combination of 3n minus 6 modes of vibration. I mean, so there are 3n minus 6 number of vibration which are independent. That's why normal to each other, normal modes of vibration. That's why I was using the pun if there is any abnormal modes of vibration or something like that. No, actually, what does that mean? That there are these 3n minus 6 individually, they are not dependent on each other, but you may, so it doesn't, so for CO2, how many normal modes of vibration is there? It's a linear molecule. So,
yes.
and there are three number of atoms are there. So 3 into 3, 9 minus 4. So there is going to be four number of normal modes of vibration. But there could be a fifth vibration, fifth kind of vibration, which is actually a linear combination of all these four.
Okay.
Okay. But these individual, so suppose there are four, so stretching, then what is there, symmetric stretching, then it could be wagging right out of the plane, then it could be something like that, right? So those motions are independent of each other, but you can always get a vibration which is a linear combination of all these four. So
Yes.
that's what my point was. One thing is that. So the question is that CO2 is actually going to be infrared active because when it will oscillate, that time your dipole moment is going to change. What about H2O?
There can be a change in time.
There
Yes, it
can
is
be
also
also a change. It is not, first of all, it is not a linear molecule. And then uh, you have to see how many uh, is that. Again, for a H2, two atoms are there, six number of degrees of freedoms are there, six minus five. Uh, no, I'm saying something wrong. Anyway, so then which of the following molecules have involved the same question? Let's us not go into that. Maybe we can check it later. How many normal modes of vibrations are there for the following molecules? We'll not calculate the exact number because we already got the equation formula. But H2O is nonlinear. H2O2 is hydrogen peroxide. Is it linear or non-linear? What do you think? It's actually non-linear. It can, I think, exist at exist like two conformers. I'm not sure, but it is it the OH bonds are actually in different planes. Okay. Uh, it's something like a book kind of a system. I will show the structure maybe in later. Some maybe later. But what about C2H4? C2H4 is ethene.
okay.
Ethene, not ethane. Ethane is C2H6.
Yeah.
It is ethene. CH2, there is a double bond between
Double bond
C.
yes. Yes.
Yes. So is it linear or non-linear?
It's linear.
No, it's it's not linear. It looks like this.
Uh,
It's non-linear. Okay.
yes.
So and linear is this CO2. Okay. Now, so that's how you will going to calculate this, huh? What about 13.23b, the last question? All of them are non-linear, right? First one is benzene, then the second one is, I'm not sure. So what is the second one? Second one, I guess they have
Toluene.
C6H6. But
C6.
toluene should have been C6H5.
Five. That's five. Yes.
Maybe they have made some mistake. Anyway, uh, then it is what? Two kind of acetylene, diacetylene, something like that. I also forget the IUPAC names. Anyway, you have the physics background, right?
Yes. Yes.
So you are not that much
That was
aware of
confidently.
the.
Yes. Yes.
Okay, okay, okay. Anyway, that is not required, but it is not going to be a linear molecule. So is it a linear molecule or not?
It's a linear.
It's actually a linear molecule. Yes. So you are going to have to calculate like that. So HC, there are four carbon and two hydrogen, six number of atoms, six three are 18, 18 minus 5 is 13. So there is going to be 13 normal modes of vibration. So you got that idea correct. That means you're that what should I say? You you got that thing correct. What are normal modes? Why they are called normal modes?
Yes. They are independent of each other. The
Yes,
normal.
those vibrational modes are not dependent on each other, and you can combine them in a fashion to get a different kind of vibration, which can be a combination of all these.
Yes.
That's the point. Actually, Professor Datta actually tells this in a very nice fashion that he gives information about some dancing. So he says that in dancing, there can be something related to your eye. There is something related to your hand movement, hand gesture, some eye gesture, some legs gesture. So individually they are each normal modes of vibration, and now when you combine them, then you are dancing. Something like he describes it very beautifully. So I learned those things from examples from him. Anyway, so the next question, 13.14a, an object of mass 1 kg suspended from the end of the rubber band has a vibrational frequency of 2 hertz. Calculate the force constant. So we need to calculate the force constant. So we just need to remember what are the equation that is related to the force constant. So one we learned is your, and that will also have something related to the vibrational frequency. Frequency, then it will be 1 by 2 pi k by
And
m. Here it is. That's why I told we're going to get a question from the mass. So one can calculate, right? So I
yes,
am not going into the this answer, but try yourself also. So the force constant. I'll
okay.
just say that it is going to be 4 pi square mu square, uh, and then m, right, or mu. And I think if we go back to the previous question, we have there is a dependence between this your uh, anharmonicity constant and your new bar. Okay,
Yes.
so there can be different kind of question that can come. We'll see what kind of question comes easier. So by this you can get the force constant for this particular problem. Now let us go to the next set of problem. Calculate the percentage difference in the fundamental vibration of uh, two kind of isotopes are there for the chlorine for sodium chloride on the assumption that their force constant are same. Again, fundamental vibration and force constant. So same equation, right? Now vibration wave number. So we need to deal with 2 pi c k by mu. And what they have said that the force constant is same, but as we are dealing with two kind of isotope of chlorine, obviously we are discussing something with the reduced
Lower.
mass,
Yes.
right? So
Yes.
reduced mass is change. So if the reduced mass is changing, so your reduced mass for this first one is 23 into 35 divided by 58, and in the second case it is 23 into 37 divided by 60. So your calculate the percentage in change. So suppose this is your 23 sodium chloride 35 Cl and divided by new bar I am discussing. So 23 sodium 37 Cl. So it is going to be, this is going to be on the numerator, right? On the right hand side, because it is inversely proportional. And then it is 23 into 35 divided by 58. 23 is gone. It is something like 37 by 30 into 29 divided by 35. Something like this will come. But how
Under,
we will,
under
yes?
root of under root. It will be
Yes,
under.
yes, yes, true, true. This is going to be under root. Okay. Now, how do you get the percentage? You just take a difference from the one. So from both the sides. So what will happen? It will new bar 23 sodium chloride 37 Cl minus new bar 23 sodium 35 Cl. The difference is in the top, and new bar 23 sodium 37 Cl, and this is going to be your if I use my calculator. This is uh, 37 into 29 divided by 30 divided by 35. 1.02 to the power. Acha, there is a power of zero point 0.5. Still, it is going to give me something like 1.0108, something like that. So maybe I can. Okay. So what do we expect? New bar of which to be more? For that, the reduced mass is for which the reduced mass is less. The first one. The first
First,
one.
yes,
So the vibrational wave number would be higher for the first one.
yeah.
So if we have to take a proper difference, then we have to take not this thing,
To
but
do this, sir, from this equation, we can say there is a difference in 1%, 1.08%.
right. There is a difference, so we can take it like this
Yes,
and something like this. Okay.
yes,
So something like it will come 0.01, and we need to no. So what was the answer you said? That what was the
one,
difference?
1.08%.
Right. So you need to multiply with 100 to get the percentage value. Yes, correct. So that's how we do it. Do this problem. And these all the problem, the screenshot I have taken from the Atkins book. Okay. So these are there in the Atkins. Physical Chemistry by Atkins. 13.16a, the wave number of the fundamental vibrational transition for the chlorine is this. Calculate the force constant for uh, force constant will acha. This is direct that you have this new bar and you have 2 pi c k by mu. So you calculate the mu. This mu bar is given.
Yes,
And how you calculate mu, because 35 Cl2, then you have
that,
this AMU, you will get the value.
yes,
So that is one kind. Whatever the next question, the wave number of the fundamental vibrational transition for 79 bromine and 81 bromine. So this is bromine, Br2, but with two different isotope. Is that calculate the force constant? Again, same question. Just the isotopes are different, so your calculation is a little bit tougher than the previous one. Earlier in reduce mass calculate, you could have cut one value. Anyway, that's one thing. Okay. Now let us go to the next question. Calculate the relative number of fluorine molecules. This is actually a good question. So whenever, so tell me this question, they calculate the relative number of fluorine molecules where the new bar vibrational wave number is given in the ground and excited state, vibrational state at these two temperature. So how would you proceed for this question?
probability function, you can determine this.
So probability of so this transition will TMI, or this intensity is going to depend on the number of population, right?
Yes,
So if calculate the number of Cl2 molecules in the ground and the fast excited state, and as there are no degeneracy, so directly suppose your uh, population of your V equals to 1 divided by P V equals to 0 is going to be some Constants are there obviously, and it is a Boltzmann distribution exponential minus energy of your v equals to 1 by kbt, right? Kbt is your Boltzmann constant, uh, divided by exponential of minus energy of your v equals to 0 state divided by kbt, and this leads to v0 by kbt multiply by exponential v equals to 1 divided by kbt. So you can actually add them up, v0 minus v1 divided by kbt, and which is actually your energy difference between the two vibronic levels, and which is h nu. We already know, right? H nu v by kbt.
So it will be minus v equal to 1 state as higher value compared to the
Sorry. So it would be minus, right? Because here this is going to be your 3 by 2 h v, and this is going to be 1 by 2 h v. So here this is going to be minus h v. So what are the things we have? We have new bar. So from here we can, energy is h c nu, or delta E is h c nu. So you know the Planck constant, you know the speed of light, and nu bar is given. So that will give you in joules. So that is your delta E, right? So this is actually nothing but your minus delta E by kBT. kB value you know, 1.38 into 10 to the power minus 23 joule Kelvin inverse, right? So this is your kBT, kB. And now you can change the temperature. You have given two temperatures. One is 298, another is 500 Kelvin. So your Kelvin inverse will go, and joule in the above portion, what you are going to get, joule into second into, now suppose centimeter second inverse, and then you have your new bar in centimeter inverse. That will cut. You are going to have your energy in joules. Joules and joules will go. Kelvin inverse, Kelvin will go. Obviously, you are taking some exponential to the power, some I would say you are taking some power of exponential, or exponential to the power that. Obviously, the inside thing is unitless, and you can calculate the ratio.
yes.
So, what do you think? A ratio would be, for which case the ratio would be higher?
This for higher temperature it will be higher.
Right. So, one can calculate individually, and then you will get the answer. Same thing would be the case for the second question, right? So, I'm not solving explicitly, because just we are looking at the problems, and you can solve it anyway. We'll give you the thing, and okay. Now, the next problem. The hydrogen halides have following fundamental vibrational wave numbers. Hydrogen halide means there is the HF, HCl, HBr, hydrogen bromide, hydrogen iodide. Now calculate the force constant of hydrogen halogen bond. First of all, hydrogen halides have the fundamental, again, the vibrational wave number is given. You are given with the isotopes. So
Yes.
again, we will use this, mu is 4 pi square. Then I think C will come into the picture if we use the new bar, right? And then actually C square also, right? And new bar square will also be there, multiplied by mu. Do you think I have written it correctly? I think so.
Both sides.
No, this is going to be K. Oh,
K.
so, no, 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 I'm right. Okay. Is it so? Uh, Mu will come. No, no, I have written it wrong. It's always better to go from the past thing. What you remember that your uh, mu bar is 1 over 2 pi c
K by
k
mu.
by mu. So we need the k value, right? So k is going to be 4 pi square c square mu bar square mu. Okay, now it's correct. Okay, so you can calculate the new bar. Sorry, new bar is given. You need to calculate the reduced mass. So from reduced mass, you are going to get something. So let us discuss the unit of force constant once for here, so that if you're doing it for other problem, you are not facing any challenge. So mu bar is kg, right? Something because you will get in AMU, atomic mass unit. So you need to convert it into kg. How will you convert? You just one a
1.6. Yes.
right. It you multiplied by 1.6 into the minus 27 kilogram.
Yes.
So ultimately you are going to something in kg. 4 pi square is doesn't have any unit centimeters, so mostly you are going to use the centimeter square second minus 2 because that centimeter why we are using because the new bar is
You are
always giving in centimeter, right? So it would be centimeter minus 2, then it is kg. So what is the unit is going to be kg second to the power minus 2. The other way to see it, like, see, your force is what? Force is always given by minus kx, right?
yes, minus kx.
Displacement into force constant. Your so let us take the modulus of this force. If we are discussing only about the unit, so this is Newton. We don't know the unit of force constant yet. We know meter, right? So Newton meter inverse. Newton is, we told you, another way to look at it is mass into acceleration, right? So Newton is kg meter second minus 2 is going to be equals to your uh, am I writing it correctly? Oh, and your meter is there, right? This is your only your Newton kg meter second minus 2 into meter inverse. So that
Yes.
is going to be your meter k into meter. Your meter cancel. I think I have made some mistake. Can you identify? Oh, I have already taken the meter here, Newton meter inverse. I don't have to deal with this meter. Did I confuse you?
No, it's normal.
Oh, yeah. So just that's how you can confirm that your unit is going to be in kg second minus 2. So that is one thing. And here, from here onward, there is another question that from the data of the exercise, this predict the fundamental vibrational wave number for the deuterium halides.
Okay.
So we are
Yes.
not going to calculate it, but what do you think? What is going to be the individual values? Are they going to increase or are they going to decrease?
You are asking about this mu will increase, so force constant also increase, and the frequency will be decreased. Frequency will decrease
See, the
because mu is
force
going to.
force constant are going to be in isotopic effect. In this kind of problem, we take a assumption that the force constant is not going to change.
Okay, if it remains constant, then this frequency will decrease because mu is going to increase because
I,
this yes, deuterium
absolutely
is
correct.
heavier compared to this hydrogen.
Absolutely correct. Absolutely correct. So the problem we faced earlier, some isotopic problem we are dealing with. So that's how you do it. We have some other problems. Oh, we have some two more. Okay, good. Good that we are not solving explicitly. Then we could not have discussed this, right? This many. So the first question, the oxygen 16O2 delta G values for the transition. Let us take delta G gives free energy. Let us take this in terms of the energy value, huh? Energy between the transitions. ej, whatever we are taking, huh? Delta G values for the transition V from 0 to 1, V 0 to 2, 0 to 3. What are these? Fundamental, first overtone and second overtone, right?
Yeah.
So these are coming at uh, so fundamental. So maybe we want to solve this question. Fundamental coming at 1556.22 centimeter inverse. Then first overtone at 3088.28 centimeter inverse. Then second overtone 4596.21 centimeter inverse. We need to calculate the new means the wave number of frequency and the anharmonicity constant along x. It has written that assume the anharmonicity constant along y is 0. Okay. Okay. Now, what is fundamental? Fundamental is 0 to 1. So now, as we need to so whenever this is given, an harmonicity constant, you are you need to determine the value. Then you know that we are dealing with, and obviously the transition from 0 to 1, 0 to 2, and 0 to 3 are given. That means the anharmonicity has been invoked. It is not simple harmonic oscillator anymore. So the energy V is it this?
No, the anonymity terms also comes
Right,
into the picture.
right. So that is Xc into V, right? So what is the energy of the zero state? That is 1 by nu V minus nu V by 4 Xc, right? What about 1? It is going to be 3 by 2 nu V 9 by 4 Xc. What about the energy of the second uh, excited vibronic state would be 5 by
5 by
2 nu bar by it is
25 by
going to 25 by 4 nu v xc. What about 3? This is 7 by 2 v minus 49 over 4 nu bar xc. Right? Now, from these two, you are going to get the fundamental. So, epsilon minus 1 minus epsilon 0, that is going to be your nu minus actually 2. So, 9 minus 1, that is 8. 8 divided by 4 is going to lead you to this and this. So, this is given already 1556.22 centimeter inverse. You are getting it, right? What I am doing?
yes, yes, yes.
From here you can get, oh, not from these two.
0 to 2.
2 minus 0. 2 minus 0 will give it you 5, 2 mu v minus,
6.
it is going to be 6, right? This is 308828 centimeter inverse. Then this 2 epsilon 3 minus epsilon 0 is 7 minus 2. This is 3v
Minus
3v
12.
bar minus 12 1948, yes, over c is 4596.21 centimeter. So you have three equations: equation 1, equation 2, equation 3, and you have two variables, nu bar and xc. So from this you will be able to calculate both the values, right? Once you, what you can do, you can uh, multiply 1 with 2, then take a minus between 2 into 1 minus 2, right? You are getting my point? Or even what you can do, you can once 3, so you can do anything here, 3 minus 2 minus 1, something like this. Huh?
Yes.
So
Yes.
that time you are going to get something in terms of minus 12 VEXC. So these will go 3V minus 2V minus V is going to cancel out. So
Yes.
plus 6 VEXC plus 2 VEXC. Uh, that is going to give you some result 4596 minus 3. Obviously, that is going to be something negative. Uh, let us do it for once. Uh, this is 2, 8. So minus 4 VEXC is going to be uh,
Sir, only solving first two equation we can get these two values because
ah, sure.
two values. Yes, no need to
Third one.
this third one. Yes.
Because what you can do, you can multiply the first equation by 2, then
Yes.
just take a difference, and that's how what that's why I'm not going to do the further. But from here you will get something about I understand about the VEXC, right? And then you can put that equation into either of the three equation, and there from there you can get the idea of only the V, right? And once you get the idea about V bar, then you
Yes.
can calculate XC.
Yes. Yes.
So with the same idea, you will be able to solve the next one. And not only the next one, the rest of these two problem also. So it is given that first five vibrational energy levels are given. So first five means 0 to 1,
Yes.
then 0 to 2, 0 to 3, 0 to 4, 0 to 5. Now calculate the dissociation energy of this molecule in reciprocal of centimeter and electron volts. First of all, dissociation energy. How would you calculate it?
This X and D are related by this
Right.
formula.
So once you get the value of, so by the previous treatment, you will be able to get the value of Xc. Maybe only using first two or the first three equations, right?
Yes.
So you don't need all five. So from there, what you are going to get, you are going to get the Xc value and obviously the V. So you will require both the values, Xc and V bar, both you will require because your, I think your uh, Xe is nu bar divided by 4 dE, something like that, dissociation energy. So your dissociation energy is, you will require V bar 4 into Xe. When you get the individual value, then you can calculate dE, right? Your dE also come, so Xe, does Xe have any unit, anomalisity constant?
Anonicity constant.
Hmm?
I don't think so.
It doesn't have, because see, you can present this thing into centimeter inverse your energy, right?
Yes.
De is
Yes.
dissociation energy, and nu bar also you can present in centimeter inverse. So Xe doesn't have any unit.
But
Okay.
I have a doubt. This
Yes.
first five vibrational energy levels. So
Hmm.
whether it means this E naught, epsilon one or epsilon two like that, or the transition between epsilon zero to one state.
Oh, no, no. These are given for epsilon 0, epsilon 1. These are given. Sorry. So these are given. Epsilon
Yes.
2, epsilon 3. These are given. So you can take the difference between them, right?
Yes.
And that will give you the transitional energies,
Yes.
or even that is not required. From here you are getting the idea, right? V bar by 2 minus V bar by 4 XC. That is your
Yes.
148186. For second one we already got 3 V bar, so for 9 by 4 V bar XC, that is your 4367.5, right?
Solving this two equation, I can
Solving
get
these
this.
two, yes, correct. You multipy 3 with the first one, and then only you are done,
Yes.
right?
Yes. Yes.
That's how you will be able to solve both the questions. So first of all, you need to, as you pointed out, you need to look at the question very carefully, that if they are discussing about the transition energy or the each of the energy levels. Those are given.
Yes.
Else it will be the question will be very simple, but we will do a wrong calculation.
Yes.
And I think I can. So you can check in the internet what is the relationship between the centimeter inverse and electron volts. I think 1 centimeter inverse is something like 0.0000124 electron volts, something like this. I'm not sure. Just check it. So
Yes.
anyway, we are going to get the answer in centimeter inverse the way we have done it. Now,
Yes.
when
Sure.
you do it, I have written it somewhere. I have checked in the internet. Um, yeah, point 1 centimeter is equal to 0.0000124 electron volts, and um, 1 eV is something like 8065.6 centimeter inverse. Either way. So that's these many question numerical problems I had. Why when you solve these problems, I hope you will be able to solve the assignment three. I think those problem also assignment three. I think the last date is tomorrow or the day after tomorrow. Just check the submission date, and we'll be able to solve those also. And if you have any numerical problems from your side, then please also uh, bring it on the next day. If you
Yes.
are finding some problem, it will be even better if you post it in the discussion forum. Then I can have a look at it beforehand, so that I will also try to solve it and come prepared.
Okay.
So if you have some problems, please share it on the discussion forum.
Yes. Yes. Sure.
And I will also discuss the the errors what we have found out in the assignment. I will discuss them with the professor as well as the TAs who are associated with that. And maybe with that we can call it a day for today. And hope to see you on the next session. I hope
Sure.
the session was useful to you.
Yes. Sure.
Yes. Thank you for joining. Thank you. Thank you very much.
Good night. Good
Good
night.
night. Good night.